We'll spend an hour talking about feature ranking, and I could have called it feature selection. It's all about, for machine learning, how do we pick the best, the most important, the most informative, the fewest number of features to work with to build better models. Now, there's a lot of other topics we could talk about in machine learning, but today we'll talk about feature selection by feature ranking. What I'll start with is a very quick introduction. Those of you who have attended these regular webinars, you're going to start getting bored of this. So I'll go really quick. I'll talk about the goal for today, what we want to try to accomplish, and then I'll get into the motivation for feature selection. People who have attended my classes before know that I like to mention the curse of dimensionality. So I like to talk about that. It's a good way to motivate this, specifically if you're dealing with a manager or somebody who's reviewing your project, your model, and you have to explain why you wanted to reduce the number of features. It may not sound great to them. We'll explain why. And multivariate analysis, just the prerequisites, and then we'll get into a variety of feature selection methodologies. There's more topics we could have covered, but we had to keep it down to a quick 1 hour. Introduction. Anyone here who has not seen me, heard from me before, I am Michael Pyrcz. It's pronounced just like Perch. I'm from industry. I have only 3 years experience in academia. I'm just trying it out. I'm seeing how I can do as a professor. It's been a lot of fun so far, though. I have practical experience, about 13 years of experience in spatial data analytics, geostatistics, subsurface modeling, uncertainty, statistical modeling, all of that. I'm very flexible. If you've got ideas going forward, if you want to hear about a different topic, if you want to change the pace, if you want to cry mercy and say, let's slow down and talk about something so we can understand it together, that is my goal. I like learning objectives rather than schedules. I'm available. I have an open door policy. I talk to a lot of people, and I'm an engineer and geoscientist. If I speak too much like an engineer or even a geostatician, and you're a geoscientist, you want me to give you a geoscience example, I do speak geoscience too. And I frequently work in this area. Now, I just wanted to comment, anybody here see my YouTube channel? Anyone see my Twitter? Anybody follow on that by show of hands? I am active. I do share. Oh, very cool. Hey, thanks a lot for letting me know. I see that 5, 6, 7. I do share a lot of content, ideas, resources online to support working professionals. So that is available to you too. Now, I just asked or gave you a lot of information about myself. Can I ask a couple of questions about you? Let me see. Now, Avi, let me ask you, who put the poll together? May I ask? Kunal, Avi?
I did.
Okay, are all of the questions together so when I launch the poll, they'll all show at once?
No, they're 3 separate polls. So if you hit that right arrow, that little caret facing downwards, you should get 3 sets.
Okay. So right now, this is the first set showing?
Correct.
All right. Thank you for explaining that to me. I do appreciate it, Kunal. We're all learning this remote teaching environment. Let me just ask you a question. First of all, what is your expertise? I talked about myself. Are you a geoscientist? Are you an engineer? Do you work in business? And we've had that. Human resources, data science. You know, last time we had a bunch of people from the mining sector. That was really interesting. So it wasn't just oil and gas. We've had people from groundwater and so forth. Do you code every day? Every day you code. Coding is a lot of fun. Coding is your life. Or do you just code sometimes to solve a unique problem? Or are you interested in learning more about coding? Do you use statistics in your job? That's great. And remember, if you use statistics in your job and you're good at it, update your CV. As far as I'm concerned, that's data analytics, okay? And that's a hot topic right now. Data science, data analytics. I sometimes use statistics at work, or I do not use statistics. And then finally, what are your expectations from this following 45 minutes? General concepts, terminology, examples, ideas, what can be done. Adopt some of this at work. We love that. We pride ourselves on the idea that we'll teach you in an hour something you can use this afternoon to add value. And you're an expert, you want to fill in some gaps. We already see we have an expert. Okay, I have most of the responses. I bought you enough time to fill that out. 36 out of 44. So I'll go ahead and end the polling in 3, 2, 1. Okay, let's just walk through this really quick. What is your expertise? I'm going to share the results. What is your expertise? And I see about 2/3 are geoscientists, and then about a quarter engineers. And then, interesting, we have some data scientists, a couple of data scientists. In the chat window, I'd be interested to hear about, what's your domain expertise? Did you originally start as a data scientist, or did you kind of merge into that from geoscience or engineering? That's very interesting to us. How did you get on that journey, for sure? Do you code? Well, what we find here is that coding sometimes to solve a unique problem is the majority, by just a slim majority. But we have a lot of people who actually would like to learn coding and would like to do more. We only have about 25% who code every day in their job. And that's pretty typical, a distribution that we see for these classes. Statistics, i.e. data analytics, frequently used statistics. Update your CV. You can say data analytics, okay? So 36%. Sometimes use statistics, majority 56%, do not use statistics, about 8%. And what is your expectation? General concepts, terminology, and limitations. We will cover that. Examples and ideas, what can be done. We'll talk about methods, and then I'll show some code. And adopt this at work. You can take the code, you could use it at work. Okay, now I'd be interested. If you're one of the experts, you're filling in gaps, why don't you let us know in the chat window? I'd be interested. If you have feedback, ideas, and so forth, if there's something else you'd want to hear about or something that can help, you may be interested in how you communicate with others. And so this is an opportunity to learn more about how to communicate your expertise. Okay, that was really good. Thank you very much, Joel. Appreciate your participation in that. Okay, so let's go ahead and talk about the goal for today. Well, I think it's aligned with what people expected. That's for sure. Want to teach you the theory and an application you can use immediately to add value. Multivariate analysis, for most of us, this will be some review, a couple of new ideas, I suspect, for some of us. Then feature selection for machine learning. And the whole idea is this: strengthen your machine learning knowledge with a strong foundation in statistics, data analytics. Okay, they're not independent from each other. That's always our goal, is to build on that. Just like we previously, what was that, a couple of weeks ago, we talked about probability in machine learning. We were building on a foundation of probability. We have to have that strong foundation. Okay, what's the motivation for feature selection? How do you explain to your boss that you want to throw features out or remove features in a careful manner? How do we explain ourselves? Well, first comment I'd make is that we typically need to build reservoir models with more than one property of interest. We do have to work with multiple features. Unfortunately, the world is not univariate. Now, this has gotten worse in recent time. And when I say worse, for a data science-oriented person, better. Meaning we need to work with more features for whole earth modeling, closing the loops. Everybody's trying to close the loops now, right? They're trying to run forward seismic on the final subsurface model so that they can test to see whether or not you match the original seismic information. Have you seen that before? There's a lot of publications on that. And what's very interesting is that when you close that loop, now you have to model the elastic, acoustic properties, densities, and primary and secondary velocities and so forth in this subsurface, things we would have never modeled before if we were just concerned about forecasting. Expanded with unconventionals. Oh my goodness. You work on unconventionals and now you got vitrinite reflectance. We never worked with that before. Geomechanical properties and so forth. It gets much more complicated. Subsurface properties include all of these possible categories. We work with, I'm preaching to the choir, as we say in Texas. We have to work with many features indeed. What is the curse of dimensionality? The curse of dimensionality. The more features we work with, the more difficult it is to visualize and to look at the data, to look at the model. More data required to infer joint probabilities. I could draw that out for you. Really, at the end of the day, we need to understand the joint PDFs, probability density functions, between all our features, really to do the job right. And that becomes impossible. In high dimensional space, you'll never have enough data to sample that. Less data coverage. If you cover 80% of the range in one feature, 80% of the range in another feature, and that would be lucky, considering the fact that we only sample 1/1,000,000th volumetrically the subsurface, you only cover about 64% in the bivariate space. And you can extrapolate that into higher dimensional space, and you realize in 10 dimensions, 20 dimensions, you don't cover very much at all. more difficult to interrogate and check the models. The models are just more difficult to understand, but you also have the issue of more likely to have redundant features. And that is a major issue on model variance. And more complicated, more likely overfit models. Well, that is a common problem with complicated machine learning models. And the final point, the final nail in the coffin for high dimensional problems or modeling in high dimensional spaces, distances in high dimensional space become meaningless. And that's very, very interesting. You can show a derivation. All you have to do is look at the volume of a sphere inscribed within a cube. And if you look at the derivation, as you go to higher and higher dimensional space, the volume of the sphere, the hypersphere at that point, will go to 0 as a ratio of the volume of the cube. In other words, space becomes deformed. All random points become almost equidistant from each other. It's very, very interesting. Okay, so I hope I've convinced you with that very brief summary that we can't work with, if they give you 100 features, it's not generally a good idea with machine learning to try to do a 100 feature model. Okay, that's going to be problematic. So let me make a confession. When it comes to subsurface oil and gas workflows for reservoirs, we have commonly been just 2 dimensions. We've usually worked with a facies model, which is critical. And then we go ahead and we build a porosity by facies model. You see that's conditional on one other feature. And then what we do is we do the permeability conditional on the porosity. So once again, these are just bivariate models. So we have in general been working in pretty low dimensional spaces ourselves. Now I could get into the uncertainty model in the subsurface, and we could talk about how that can be high dimensional. But in general, we haven't been solving a lot of high dimensional problems. Okay, so let's go ahead and cover some prerequisite statistics, some multivariate statistics. Now, there's a purpose. We're going to spend probably about 15 minutes on this, and it will provide us the basics we need to get into some of the feature ranking methodologies that we're about to cover. Okay, now, remember, any questions or comments at any point as we go along here, go ahead and just put them into the chat window. Happy to discuss any concepts at any point. Want to make sure everyone's following along with us. Let's talk about bivariate analysis. It's illustrative, or it can definitely help us understand the issue of trying to project into lower dimensional spaces, or the issue of what we can miss if we don't visualize our data in its full dimensionality. Take this example right here, porosity, permeability. This is the book from the book of Pearson. And what you'll see right here is that if you were to look at that data set and you were to project it into a histogram of permeability, a histogram of porosity, I hope we can all acknowledge that we would be missing the most important story here. We would fail to see that there's these specific patterns or clusters in the bivariate space. And if you look carefully, what you'll see in the legend, that those are tied to grain size, that these are trends in porosity and permeability unique to each grain size. It could be fabric of the rocks, cementation. There's a complicated signal there, collapsing into a lower dimensional space, and we will lose that signal. So it is very challenging to try to understand high dimensional space, specifically when it comes to just trying to, what we would call marginalizing or collapsing it to lower dimensions is usually not sufficient to understand it. Now, when we look at the relationships between features in a higher dimensional space, there's all kinds of different patterns we can observe. And some of those patterns would include things like linear relationships. You look right here, if you try to draw what we call conditional expectation line, or you could think about it as some type of model fit in a general sense, that you could say there's a linear relationship between acoustic impedance and porosity. But if you look over here between porosity and permeability, clearly it's a non-linear relationship. Now, one of my favorite words in the whole world is homoscedasticity or heteroscedasticity. And now when we look here, we can see that if I was to split this data set, I put my hands up on the screen, and I only look at a limited window of acoustic impedance, I hope we can acknowledge that the conditional variance or dispersion doesn't change too much as we move along that line. That's homoscedasticity. Now, if you look at this example right here, clearly there's a higher degree of variance in permeability for the high porosity values and very little variance for the low porosity values. These are all important features we can observe, and they can complicate or they may be essential to our method. We're about to describe partial correlation coefficient, which assumes linear homoscedastic relationships between the variables 2 by 2. So it's good for us to think about that. Here are some other structures we can see, of course, going from categorical to continuous features, and we often see constraint relationships. Now, a really good example of a constraint relationship is if you have some type of sum one constraint. In other words, you have a situation where you have mineralogy and the proportions of the rock, and the sum of all of them is 100%. Well, clearly you're in a situation where you'll have some type of constraint, usually a line over which you cannot exist because you would exceed one. You would exceed the volume allowed. So there are all kinds of possible constraints we can encounter. I'm sure everyone here has heard of the Pearson's product moment correlation coefficient. Here's the equation right here, commonly known just as the correlation coefficient. It's a measure of the degree of linear relationship. It's commonly used all over the place in modeling. The calculation is really interesting. If you look at it, it's the product of the difference between the first feature centered by its mean and the second feature centered by its mean, and it's standardized by the standard deviation of each of the features. Now, just for clarity, if you remove the standardization, it becomes the covariance. And the covariance is quite commonly used. Covariance functions and concept of covariance are commonly used within geostatistics, but really just think of it as a non-standardized correlation coefficient. Now, to those of you who want to kind of intuitively understand what covariance is, it's actually really easy. All you have to do is compare it to the variance. I think everybody has a good intuition on what a variance is. It's a measure of dispersion. In fact, if you look at it, the equation for the variance is often shown with a square. It's the basically ignoring degrees of freedom. It's the average square difference between values and their mean. Now, if you take that square and expand it, you have these two components right here, and you replace one of them with a second feature. I hope you can see that the variance is extended to covariance. In other words, how two features vary together. I think that's a really good intuitive way, a hook, to grab onto the idea of covariance by thinking about just replacing one of these components with another feature once we expand that square term. All right, how two features vary together. Now, it turns out that the correlation coefficient can be quite sensitive to outliers and slightly nonlinear behavior within the data. And the way we can deal with both of those, outliers and monotonic nonlinearity, are to go to the Spearmint rank correlation coefficient. To be honest, I really feel like people don't use Spearmint enough. It's quite a bit more robust. Just like the correlation coefficient, it ranges from -1 to +1. The only difference, if you look at this equation right here, and if I went back here, I hope you can see they're the same, except for every time I have X or Y, I replaced it with this RX or RY. What R is, it's the rank transform of the data. Now, let me demystify this idea right here really quickly. If this was your original data, 1, 4, 6 through 20, and if you replace the values with their rank order, in other words, the largest value would be equal to n, the number of data 6, and the smallest value is equal to 1, then you would have, in fact, a rank transform of that original data set. Now, if you replace the data with that, what it does, in fact, is it will deal with outliers, and it will actually linearize if you have monotonic nonlinear behavior. Now, Pale, I don't know how to pronounce the name. You asked if I would use Spearmint or Pearson. You'll find that I often use both, and we're about to use both, compare them to each other to interpret the data set. Now, when it comes down to it, there's a lot of theoretical like applications where the theory requires the Pearson product moment correlation coefficient. A perfect example is if we start thinking about the correlogram or autocorrelation. Those that they need to be the Pearson product moment correlation coefficient for it to work. Okay, so but in general, we're going to use both when it comes to feature selection, and then we can use the comparison as an interrogation tool. I really like that. I think that's a good way to do it. Let's go ahead and take this example right here and just make some general interpretations of the Pearson product moment correlation coefficient. Here's an example right here, high correlation coefficient, low correlation coefficient right here. And we have an example right here. Now, I want you to notice something about it. It is a quadratic. It's a perfect quadratic with no error. And the result is you have a limited correlation coefficient. It's not 1.0. Now that's interesting because people often mix that up. They think correlation coefficient tells you the degree of predictability from going from X to Y. If that was the case, this should be equal to 1. But it's not. It's telling you about the degree of the linear relationship, and it is disrupted by this curve right here. Now there's something very pathological about the correlation coefficient. If you take a random set of data, literally random draw between this interval on X, this interval on Y, and you plot it, and then you add one outlier point really far away. Look at that, correlation coefficient of 0.95. And guess what? If you keep moving it further and further away, it gets higher and higher. This is very dangerous with the correlation coefficient if we're doing correlation analysis. And look at this. If you look at the quadratic over a symmetric interval, going from a negative to a positive value, if you have enough data sampled on that interval, it will approach a 0 for the correlation coefficient because that's completely nonlinear. And it's also not even monotonic. It is going down and coming back up. So it really does start to mess up. Now I have a question here. So if outliers are removed during preprocessing, then Pearson correlation coefficient will do. I would agree with you. Dwalit, I'm sorry about the pronunciation there. I would agree with you. It's outliers and it's nonlinearity. Those are the two things that can interfere with the correlation coefficient. So if you have a reasonable linear relationship and you treated the outliers, and you said removal, there's multiple things we can do with outliers. Removal with good defense, right? Or maybe separation into a distinct population is something we often do in the subsurface. That's fine. Then that sounds like you're on the right path. Now, I just want to make this statement to everybody on the line. I am not going to say anything negative about religion, okay? But did you guys know that churches cause crime? Has anyone ever heard that before? Actually, here's an example right here. I should have provided the citation. It's taken from a book, but I do have number of churches increasing, number of crimes committed increasing. What do you think? Anybody want to suggest what's going on here? Both are related to the, thank you very much, Lori. They're both related to the magnitude of the population. In fact, small cities, medium cities, large cities. And if you looked at the correlation within each one of these, you'd find out it's within error. It's random effect. And so clearly churches are not causing crime. We have a confounding feature that we have not accounted for. We need to control for all the other features to really understand causation. We need a true experiment. And so let's remember, correlation does not imply causation. And this happens all the time. Has anybody here ever been to the website? Has anybody ever been to the website spuriouscorrelations.com? Anyone by show of hands been to that website? Anyone? It's awesome, isn't it? Yeah, I see a bunch of hands, 6 different people. Check it out. The website is down today. They should have it up again shortly. They had a problem with some configuration. But what they do is they data mine from publicly available databases where you don't have enough samples. And then what they do is they look across, and what they find is that eventually they're going to create or find an artificial correlation. It's going to happen. It happens all of the time. And so here's an example right here from the state of Maine, where they showed, in fact, that margin causes divorce. Now, the objection I have is that I often feel like maybe divorce might cause margin. I'm not sure. I'm not sure which way it would be, but we got to be really careful about that for sure. In fact, what I did for fun was I took Python and I made this interface. I hope everyone can see this. Let me just shrink it a little bit. Right here. So what I did was you can control the distribution statistics, the number of samples, and the number of features. And when you do that, what you can find is that if I only have 4 samples and I draw randomly from this Gaussian distribution, look at all the red and blue squares. Those are randomly occurring correlation coefficients that have an absolute value, negative or positive, greater than 0.8. And that many people would consider that a significant correlation. So in other words, you can see that as you increase the number of data, do you see what's going on? Increase the number of data, I slowly start to drop and have fewer spurious correlations. It's a statistical significance problem for sure, and we should be putting significance on our measures. Anyway, I thought that was kind of a fun example to show. All right. If you want to prove to yourself some of the issues with the correlation coefficient, please go ahead and try doing this. Create a random cloud, create a random point, offset it, and calculate the correlation coefficient, and you'll get an example like this. If you want to see the difference with rank correlation coefficient, here's the original data set. Here's after I do the rank transform. You see what happened? 50 data, 1 data up there, 51st. And that data is now 51 by 51 is its new value because it's replaced with the rank. And it becomes like just incremented by 1 above the maximum values in the other part of the subset of the data set. All right. Here's an example right here of the correlation coefficient equal to 0. And if you take a range of 0 through 1, you get a correlation coefficient of 0.96. If you take the rank correlation coefficient, it deals with the nonlinearity. And the result is you get something that is a rank correlation coefficient of 1. Now, anybody here ever heard of partial correlation? Anyone on the phone? This is going to be one of the major methods I show you. I see 2 hands up. That might be remnants from previously. Anybody ever heard of partial correlations? 3, 4, 5, 6. Thank you very much, guys. I do appreciate the participation. And I'm curious if I recognize some of the names. I do recognize some of the names. I think some of us have talked about it, but I see other people also. Okay, partial correlation. This is really cool. If we're going to do rank correlation and Pearson correlation, let's look at a method that can take X and Y, two features, and can control for the influence of the other confounding features. So we have Z M minus 2. In other words, we take an X and Y out, and now we want to control for all the other M minus 2, where M is the total number of features, minus 2 because we took X and Y out, all those other features. What are we going to do? This is the process. It's very cool. You perform linear least squares regression to predict X from all of the confounding features. Then you go ahead and you can estimate X with that. So imagine this is multiple axes for all of the other features. This is not just one feature here. And we predict X given all of those. Then what you do is you perform linear regression. You predict Y from all of the other features that you want to control for. And so we get this, Y predictions, Y star, given all the other features. What do you do next? You calculate the residual, the X values minus the prediction model for X with all the confounding features. You do the same thing for Y. You have removed the influence of all the other features. What's the next step? You take that residual of Y and that residual of X and you correlate them. You calculate their correlation coefficient. This is called partial correlation. It's very, very powerful. Now, let's also look at an example of matrix scatter plots. I always recommend that if we're going to do feature selection. We're looking for different types of relationships, constraints, nonlinearity, and we're acknowledging that we're not able to see the high dimensional space. We're only seeing 2 by 2 at a time. And that is quite a marginalization, but at least we learned something. In addition, for partial correlation coefficient, it assumes bivariate, 2 feature at a time, Gaussian distributed, or at least linear homoscedastic, mostly, not too pathological. Okay, the other thing too is I am a big fan, anyone who's taken my classes knows that I do like just plain old frequentist approach of just calculate the joint probability if you can. This is a joint probability density function. We can look at it. We can see the form, the features, the structures, the homoscedasticity, the nonlinearity. You can see it directly. When possible, I like to look at PDFs, but as we mentioned, cursor dimensionality, the sampling problem, you generally can't do that for a very high dimensional space. You can just do that in kind of lower dimensions. Conditional probabilities, we can summarize. Often you see a really ugly scatter plot where you have so many data and it just looks like somebody spray painted the chart and you can't really make any sense of it. I like doing binning across one of the features and calculating the conditional expectation, the conditional P10, P90, or upper and lower quartiles. I think that's a great way to look at our data. I recommend it. Okay, let's talk about feature selection. Let's get into some methods. Now, we've already covered prerequisites, so we can go kind of quickly on some of this, talk about some interpretation cues, and then we'll jump in the code and I'll show you how to get it done, okay? And at the very end, we're gonna have a test. Okay, I hope you guys stick around for the test. There are many different ways that we can do feature ranking in order to assess which are the most important features. It's good reason to be selective. Throwing everything into the model is not a good idea. In general, the best, fewest, most informative features are the most useful. Now, let me just remind you around the motivation and the issues around the cursor dimensionality. I put it here just to remind us. It's basically what I said before. What are the methodologies that I'm going to discuss for feature ranking here today? Well, I think that it's great to use a wide array approach, use multiple methods, interrogate, interpret, use them as lenses to be able to explore the subsurface. And it's a very good question. The more features will overfit the model. And I would agree with that. In general, we could say that if you use more and more features, it tends to increase the parameterization of the model and therefore increase your opportunity for overfit. I think that is one of the reasons that I try to drive to a lower dimensionality or fewer features in my model. Now, let's go ahead, and the types or wide array approach for feature ranking includes the following metrics. Visual inspection of the data distributions and scatter plots. I think that's always a good idea. We know that. We need to look at the data as much as we can. Statistical summaries, model-based, and the final method that I'll show is recursive feature elimination, which is a really cool methodology to do feature selection. It's like doing a dress rehearsal or many dress rehearsals to building a model. Let me just make a comment, because everything I'm going to talk about from here on in is going to be statistical data analytics approaches. Can I first just offer a word of support for expert knowledge? We should not neglect expert knowledge. I had the case of a student in one of my classes try to build a circuit model for flow, and they wanted to eliminate permeability. I hope everybody on the line can acknowledge that that would sound like kind of a silly model. That indeed, no matter what was going on with your data, that's probably more of a statement of data limitations than it is about the best features to work with. We need to always use our domain expertise to help improve our judgments in this. Now, if we have additional information about the physics, often that's very powerful. For instance, if we want to work with a subsurface prediction and we know rock quality index can be helpful, well, that's great. That's a known relationship between porosity and permeability, and we can combine the features that way. Engineering or physics-based or geoscience knowledge-based feature feature combinations is probably a great way to deal with feature ranking and selection. Now, let me just talk a little bit about visual inspection. Multivariate work, we should definitely start with univariate analysis, look at the bivariate, look at the summary statistics. What we're looking for, are there issues with the data? If the data has significant issues, well, here's the problem. What good is any statistical analysis for feature ranking if your data already had lots of problems? And so we're going to look through the data and make sure that we can trust the features, we can trust our analysis. And remember, 90% of our effort is data preparation. So that needed to be done. And if we do have issues, we need to go back and fix these issues. So in general, visualizing the data, looking at the summary statistics across all of the features, this is the data set we're going to be working with, an unconventional data set. And then you can look for, do we have issues with coverage? All of our data have values. We have complete coverage here. That's good news. Do we have skew in the distributions? You can look at the mean versus the P50 to assess that. You can look at the max versus the P75 to try to assess whether or not we have some extreme values and so forth. Univariate distributions are always a good idea to look at. We can assess the shape. Many of our methodologies have assumptions about the type of distribution. In addition, we're always concerned about outliers, and looking at the distribution, we can see that, or in the subsurface, mixing multiple populations. That happens all the time. We can take this opportunity to assess our data, look at the distributions, check for outliers. You could do something quantitative like Tukey's method for detecting outliers. I'm a fan of more multivariate types of approaches for sure. We can look for multimodal behavior. We've talked about this before. You can do the bootstrap to assess for the uncertainty or significance in the shape of the distributions. Now, I think it's a great idea to do matrix scatter plots. I've already talked about this, so I'm not going to spend a bunch more time on it, but looking for nonlinearity, heteroscedasticity, and so forth, we can invalidate certain modeling assumptions, and this may also funnel us, force us to go down a certain path or avoid other avenues. So this is important for us to assess. Now, in addition to that, a pairwise covariance, we've already talked about that. We already know the equation for it, but we're going to be concerned about covariance. I see way too many people use it. And what I'm finding, in fact, is that the covariance measure itself is way too sensitive to the variance of each one of the features. In fact, if you take the expectation of covariance, or if you take the expectation of the variance, and you work out what would happen if I apply a scalar to my feature, just an arbitrary number, and that happens all the time. The difference between porosity and percent versus fraction is 2 orders of magnitude, a scalar of 100. Turns out that's going to change the magnitude of the variance by that number squared, 10,000. So you can see the magnitude of the covariances are really just dependent on the variances. They're not very useful to us, and it motivates us to use pairwise correlation coefficients. Of course, we remember that the measure of the linear relationship, and they're sensitive to outliers, and even monotonic nonlinearity can impact them. And so we use the rank correlation coefficient to clean that up a bit. And we've already talked about that. Partial correlation coefficient, just a reminder of that, we can do that too. And finally, when we're done, we can look at results and make comparisons and interrogations. Now, what I'm going to do is I'm going to go ahead, I'm going to open up some code, because I don't want to talk too much about these methods without showing them. And I will add recursive feature elimination and so forth on top. What I have here is one of our example workflows that we have on our learning management system. And we're going to go ahead and we're going to import some packages. Let me ask, by show of hands, how many people have used Jupyter Notebooks before? 15, 16. Oh, we got to 20, 21. Okay. To the remainder, let me just suggest that these Jupyter Notebooks, what they do is they allow us to build very nice prototype workflows. We have multiple blocks that are Markdown. It's a watered down version of LaTeX. It allows us to put together equations and links and everything so we can make really nice documentation. Then we have code blocks. We can go ahead and import packages from Python. And now we harness the world's brilliance. I wrote a function right here. to do partial correlation coefficients modified from a function available online. And we have, now we run that, we get partial correlation coefficients are available to us. We can go ahead and load up a data set. I have an unconventional data set I'm going to work with. It's synthetic, so I can share it with anyone in the world. Anyone can use it. It's not a bad data set. And we have the well-indexed porosity, permeability, acoustic impedance, brittleness, TOC, vitrinite reflectance, and production and MCF-PDs. Okay, let's do some feature ranking. Let me demonstrate this to you. Let's start with some summary statistics. If anybody says, I'm not going to do Python, I would rather just go ahead and use Excel, just show them this one line of code. You just run this one line of code and you get a table with all the summary statistics. I think that's a great way to summarize working in Python or even R. I've done a lot in R, of course, and it's very powerful. One line of code, you can get a lot done. Now, I noticed some negative values in TOC. I'll do a little bit of feature engineering. It's a truncation, and I can clean that up, check the result, and I've just dealt with that. Now, you've got to be careful. We're going to truncate like that. Let's go ahead and set some minimum and maximum values, some names for the axes, and we're ready to go ahead and look at some univariate distributions. Very, very easy to do. Very nice histogram plots indeed. And we can look across. Anybody here having deja vu? This is exactly what I showed in the notes when we were just talking about evaluating these distributions. So it's what we're talking about before, just going ahead, looking at the distributions, assessing the reliability. Are there issues? Are the distributions highly skewed? Will invalidate a calculation that we may want to use. Now, if anybody's used Seaborn before, it's a package in Python for statistical visualization analysis that's actually really, really powerful. Takes a little bit longer to run, but once you run it, it's worth it. Here's the example of matrix scatter plots. I love doing this. I invite you, anytime you work with a reasonable number of features, please do this, acknowledging that you're only seeing 2x2 relationships. You're not seeing the 7, 8, 9 dimensional relationship. A lot could be happening, like those striations between porosity and permeability. Something like that could be happening in higher dimensions, and we would not understand it from these plots, okay? But we can assess whether or not we have bivariate outliers. Are there specific cases that seem unusual that we should be looking at first before we do any type of correlation analysis? That will impact our correlations. If you want to do covariances in Python, very, very simple. In fact, what's amazing is our data frame object that provided us with the ability to store and work with tabular data actually has a function for building a covariance table directly in it. And we'll go ahead and we'll extract from that just the column of covariances. I hope you can immediately see the issue with the magnitude of the covariances. They can be a little bit sensitive to the variances. So we can go ahead and do correlations. These are Pearson product moment correlation coefficients from -1 to +1. You have those right there. Now, I like the best way I think to view correlation coefficients is with a correlation matrix, and I've color coded it here. I've actually assigned a threshold where all the white colors represent correlations that are too close to 0 for me to be concerned about them. I'll consider them to be insignificant. You can go ahead and use Bootstrap to figure out what level that is given the amount of data you have. And then you can go ahead and look through here and see, oh, okay, there's an interesting relationship. Permeability and porosity seem to be highly redundant. TOC and acoustic impedance seem to be redundant and so forth, negatively correlated though. You can go ahead and do the Spearmint correlation coefficient calculation right here. Pretty straightforward. We use SciPy stats. SciPy is a really great package for doing scientific computing, and Python, and we have stats is a module there for doing a lot of really great stats. Very powerful one-line code to get lots done. I do a lot of hypothesis testing and so forth with it. Let's go ahead and do partial correlation. I made a function and I declared it above to be able to do that. Let's go ahead and run that. Now, once we've run our partial correlation coefficient, I want to show you, this is everything we were working for right here. This is our procedure for statistical feature ranking. Here's porosity through vitrinite reflectance over and over again on all of the plots. Here's the covariance, the correlation coefficient, Pearson product moment, rank correlation coefficient, partial correlation coefficient, and I did not cover the semi-partial. I'll leave that go for right now. We don't have the time. If you look through here, you can start to make interpretations. Anyone by chat window, which ones of these features do you think are most important? Because all of these are related to production, right? So which one of these would be most important to predict production? Anyone with any ideas? Porosity. Hamza says porosity. Where are you looking? I'm looking across the whole thing. I'm agreeing with you. Strong porosity correlations across the board. Let's discuss the differences. Going from covariance to correlation coefficient, differences are showing the impact of the differences and variances. James says permeability. Let's check that out too. Correlation coefficient, porosity, permeability look very good. Go to rank correlation coefficient. Do you see the difference? I don't see the difference. What does this tell me? It's not sensitive. In other words, this data set is not being disrupted by outliers and nonlinear relationships. It's doing pretty well. And I think that's excellent insight. That's why I do them together. Partial correlation coefficient, check that out. Porosity and permeability both fell. Why did they both lose importance? Less departure from zero. Let's go back here and take a little quick peek. Look at the correlation coefficient between porosity and permeability. You see that? What's going on there? They're highly correlated with each other. Okay, so this is fascinating. What it tells you is that what we're seeing with this measure of partial correlation coefficient is that they don't have that much unique information. They were leaning on each other, so they both got demoted. It's super awesome. Very, very cool stuff. Okay, and Jeff, thank you very much for the insight on porosity. We always appreciate expert-based, physics-driven interpretation of the data. That's a great idea. All right, let's go ahead. Let's talk about, we can do a Gaussian transformation. We can repeat the process. That's a good idea. Look at feature standardization. Specifically, let me just show you here. When it comes down to the relationship between porosity, permeability, and all of our various features, we got to recognize the fact that the partial correlation coefficient, our tool of choice here today, I'm showcasing it, is expecting linearity, homoscedastic relationships bivariate. And I hope we can look through here and see we do have some violations. Specifically, brittleness is a bit of a nightmare. It has a sweet spot in the mode there. It's non-monotonic. So we got to be careful about that. All right, let me just continue down. What I want to show you is that we can also consider conditional probability plots and conditional distribution plots. I think it's a great idea. You take the data set, you divide it into low and high producing wells, you look across the features and you see how the conditional distributions change. That's very, very valuable. That helps us with our interpretation. In this workflow, I include mutual information. I don't have time for that, but I would like to talk about mutual information. We'll have another time where we'll talk about it. And I make comments about feature importance through a variety of machine learning methods that allow for that. And I do demonstrate recursive feature elimination. But given the time, I'm going to finish up right there for today. Now, what I wanted to do, though, and this is important to me, I want to go ahead and ask a couple of questions. Let's go. For those of you who want to stick around for a couple of minutes, this will be fun to see what you retained from this, 50-minute discussion here today together. All right, everybody see this? Here's some questions on multivariate analysis first. For features X and Y, how do you convert a covariance to a correlation coefficient? Do you multiply by the product of the standard deviation of X and Y? Do you transform the features to Gaussian? Do you divide? Now, is everybody able to see this poll?
Yep.
All right, you're able to see the poll. Excellent. Do you divide the product by the product of the standard deviation of X and Y? Do you divide by the variance of X? What is the minimum and maximum possible values for correlation coefficient? Infinity to infinity, -3 to 3, kind of like Gaussian almost. 0 to 1, sounds like min-max normalization, -1 to 1. You calculate the product moment correlation coefficient and the rank correlation coefficient, the Pearson and the Spearmint. product moment correlation coefficient 0.95, the rank is 0.15. What's going on? Outliers are inflating the Pearson correlation coefficient, the product moment. Difference in variance between the two features. Difference in means between the two features. Other features interfering with the product moment correlation coefficient. And finally, the last question, why does correlation not equal causation? Correlation is sensitive to outliers. To demonstrate causation, we must control for all other features variables. Causation is a Bayesian concept. Correlation is a frequentist concept. That sounds like an argument waiting to happen for sure. Or correlation can be negative, and negative causation is irrational. It does sound irrational, doesn't it? Okay, we got 15, 16 responses. I'll go ahead and give you all just another 10 seconds. 8, 6, 4, 3, 2, 1. End polling. Let's share the results. And let's look at it. For features X and Y, how do you convert from a covariance to a correlation coefficient? Divide by the product of the standard deviation of each. It's a standardization by their standard deviations, and that's what forces it to be between -1. Good. I notice I did catch a few with the multiply by. That was tricky. I know I'm a professor. I have to give kind of tricky responses to test people's knowledge, but I appreciate that. What is the minimum and maximum for correlation coefficient? Nailed it. Nailed it. -1 to +1. -1. Is that a high degree of correlation? Anyone on the line by chat window, if you get a -1 correlation coefficient, is that a high degree of linear relationship? Maria says yes. Lori, Hamza, everyone. Yes, yes, yes. Very, very strong. It's just a negative relationship, right? Goes in this direction. Thank you very much. You calculate the product moment correlation coefficient and the rank correlation coefficients. The product moment correlation coefficient is high. Rank is low. What's going on? Outliers are inflating the product moment correlation coefficient. Exactly. That's it. And we showed that. Random data, one outlier, we got a very high correlation coefficient, but it was more reasonable for the rank. Okay, and why does correlation not equal causation? To demonstrate causation, we must control for all other features. The way we say that is a true experiment. You change one thing at a time, right? Okay, that's the best we can do. Causation is very difficult, everybody. I don't suggest it's an easy thing to do. I want to go ahead and just share another set of questions. This will be just a few questions right here. Now, don't answer question number 3. We didn't really spend the time on the B and beta, but go ahead and just answer the first 2 questions if you don't mind. Select the option below that is not an aspect of the curse of dimensionality. More difficult to visualize, the curse. Less coverage, biased estimates, more likely redundant features. What is the curse of dimensionality? Which one of these is not part of the curse of dimensionality? What is partial correlation coefficient? Correlation coefficient after the rank transform. Sounds familiar? Covariance divided by the product of the standard deviations, correlation controlling for all other confounding features, and the same as the Pearson product moment correlation coefficient. Okay, the answers are coming in. Thank you very much. I see I've got a couple of responses. All right. Oh, they're starting to fly in now. Thank you very much. Awesome. Now, there was a question or comment here. So far, Lori said, so far, this analysis seems to just tell us what an expert already knows. I appreciate that. I appreciate the confidence. I appreciate the insight. And what I would say is this is what I hope. I hope that expert domain knowledge of the physics, the setting, and so forth should all be complementary. I look at statistics as a new lens to see the world, but I think we should be looking through all of the lenses and putting together a consistent picture with all of them. Okay, so let's go ahead and look at the responses. Select an option that is not the curse of dimensionality, not an aspect of the curse of dimensionality. Biased estimates. There is nothing that says that we will be systematically biased due to being in a higher dimensionality, not with respect to our predictor, but we definitely have issues with less coverage, more difficult to visualize, and more likely redundant features. That was perfect. Thank you very much. What is partial correlation coefficient? Did I trick you? Correlation controlling for all other confounding features. Yes. And you see how I got tricky with the other ones. The first one is the rank correlation coefficient, and the second one is the correlation coefficient. I was just being a bit tricky with the definitions. And people challenge the B versus beta coefficients. This we should have, we'll get into next time. But the idea with beta is you use a multilinear regression, but you work with standardized features. The features are standardized for beta coefficients, which shows me we have some experts in the group for sure, people who know about these methods. So I appreciate that. Okay, I'm going to simulate the idea that I've dropped by and visited your company or your, professional association. I'll hang out here. And have any discussion. If anybody wants to talk, I'm happy to discuss. Otherwise, anybody here with us in the States, have a happy American Thanksgiving. I'm Canadian. We already had our Thanksgiving a month ago. Yeah. Or any other comments or anything. Yeah. Good. Yeah, so there was a question about PCA. I see two opportunities for sure: feature selection and feature projection. And when we teach about dealing with feature engineering, we spend a lot of time talking about principal component analysis, multidimensional scaling, random projection, which is a method that's used more with real-time information. We get into all of these ideas because clearly, one avenue is to project. I like a combination. I think sometimes we can eliminate some features right off at the start, and then we can use feature projection with the remainder. It's a fascinating thing. I'll tell you what, I did a recent example to assist with a company, and I looked at multidimensional scaling. It was fascinating what we could see in a two-dimensional space for a very high dimensionality problem. It was really, really cool how we could interpret. Okay, thank you very much for the question. Any other questions?
So I have a question.
I'm curious. Oh, Michael, please jump in.
Sure. So yeah, thanks for the overview.
Are you off mute?
This is great. I think so. Can you hear me? Maybe you can't hear me.
All right.
I was working for a second there.
And I see some comments in the Q&A window too. I was looking at the chat window. Good. Bibliography, some other resources to learn more. Very good question, David. I appreciate that. There is a lot of good content that's available. Now, of course, for this Datum event, I'm going to mention, go ahead and sign up and get access to our LMS, our learning management system. We've got a lot of content. We've got a lot of recorded videos. We've got a lot of example code, well-documented examples to get started. So go ahead and jump in on that. Check that out. But there are an amazing number of resources available to you for sure. Also check out my YouTube channel. I'm sorry, I'm shamelessly self-promoting here. Okay. Any other questions?
Michael, can you see Michael?
Hey,
Hardy's
thank you
question?
very much. Hey, Don, nice seeing you. Nice seeing you. Take care, eh?
Hey, Michael, can you see Michael Hardy's question?
And I do appreciate your use of the term entropy. And that's closely tied to the idea of mutual information, the degree of information sharing between multiple features. In the workflows that we've put together, we include the straight use of mutual information. We also use the minimal redundancy, maximum relevance types of summary statistics, and the recursive approaches, where you selectively or you recursively remove or add features and assess the MR measure. We show all of those types of workflows. I think those are very useful. I've seen some recent work with SHAP, where which is really powerful too, to try to assess the information from each one of the features and see their relative importance. Yes. Yeah, Michael, that's a great critical question. I appreciate your question about, kind of what next? What do you do next? And it's really interesting, right? We can assess overall that the interpretation, the wide array approach, to me, is that I use multiple approaches, multiple avenues of investigation, expert knowledge, analysis of the reliability of the distributions, the structures, the forms, feeds back into data engineering and data preparation. Then I come back again and I look at my statistical measures and I walk through them and I interpret them jointly. And then by doing that, I can assess, for example, if you can still see my screen, this example right here, we can understand why both permeability and porosity fell with the partial correlation coefficient. We can also understand that we're not being disrupted by nonlinear features or by outliers because similarity between rank and correlation coefficient. So for my final assessment of the most important features, given this line of questioning, given this available evidence, I would definitely start looking at the fact that porosity looks like our big hitter. In addition, permeability initially looked good, but I suspect it has such a high degree of redundancy, linear relationship with porosity, I can probably live without it. And I start to realize some other aspects too, is that total organic carbon looked like it was really impactful. It, in fact, when you control for the other features, it flips its relationship with production. Isn't that incredible? But it also becomes less significant. Now, what I would also do as the next step is I would bootstrap and put significance lines on this. And I would start to assess whether or not the correlations are significantly different from zero. And then from there, I can make choices. I can definitely at this point produce a reasonable rank order of features to decide a reduction in variance. Okay, good. Other questions? Oh, Michael, you were having an issue with your microphone. Okay, but thank you very much for typing in the question. We appreciate you and good to see you again. Good, good. Awesome. Any other questions? I think I saw Ben on the line. Ben, welcome. Thank you very much. Good to see you. Now, Walter, this is a really good question because we face a lot of optimization challenges in machine learning. Now, when we cover and talk about methodology, specifically what forces us to get into optimization are two issues. The first issue is that when we go to L1 norms and more complicated machines, we definitely lose our analytical expressions. We need to optimize to get the parameters, model parameters to train to the training data. And there we discuss various optimization schemes. We do tend to kind of focus on stochastic gradient descent types of approaches. Now, when we talk about GANs, what's very interesting is you get into an adversarial type of a training situation, which to me is fascinating, really, really interesting when you look at this whole idea of an adversarial configuration, loss functions where you have two agents that are effectively competing. I'm not sure if competing is the right term, but learning together in a very interesting, in a way that there's a trade-off between them, which is fascinating. So, some of the aspects of machine learning definitely get us into that. Now, of course, things get even more meta when you start dealing with more complicated machines and trying to optimize their architectures and their hyperparameters, and that becomes higher dimensional. That's for sure. All right. Let me just ask, since I'm Canadian, any Canadians join us today? Hey, Walter, no, thank you for the question. Appreciate that. Great question. Thank you. Oh, from India. We have somebody from India. Thank you very much for joining from India. Very cool. Now, I'm going to assume that Thanksgiving hasn't been exported there. It was to Canada, but a month earlier. I guess our snow comes earlier in the winter. Okay. Hey, thank you, David. Thank you for participating. Appreciate it.
All righty, Michael. I think we can shut this down. Thanks for all the help today. It was a great class.
We got a hockey fan, Luis. Very cool. Okay. All right, Kunal, what do you say? Hey, thanks a lot, James, for participating. Yeah, I think the 1 hour is fun. Yeah. Okay, so we're going to shut down now. I got to run to my next meeting. Professor work, never ends. Kunal, thank you very much for your help behind the scenes. Appreciate it. And Avi, if you're still on the line. Hey, see you, Don.